My name is Alex Razoumov. I'm a visualization coordinator, a support specialist for WestGrid. So I handle all things related to visualization, and I do quite a lot of teaching, which I'm going to cover in the next few slides. Today's webinar is going to be about scripting and other advanced topics in VisIt visualization. And I apologize for my husky voice. I have a small cold, so I'll try to speak louder. The slides for this presentation are available online, so I put the link into the title page, so bit.ly/VisIt scripting. If you open that in your web browser, it will download a small zip file, roughly 1 megabyte or so, really small. And when you uncompress, extract files from it, you will find the slides for this entire presentation, as well as 15 or 20 smaller scripts that you can run either during the presentation or most likely you can play with them after the presentation, since you want to see what I'm doing on my screen. So I'll show a lot of live demos on the screen during the webinar. And I don't expect you to repeat everything during the webinar, simply because there's no time. But feel free to play with these, and after the session. And if you have any questions, just send me an email. I'll be happy to answer them. So the main data file that I'm going to play with in most slides is called noise.silo, and it's already included into VisIt on all 3 platforms: Windows, Linux, Mac. And to search for it, you can, for example, have a Unix shell, or I don't know, DOS shell. You can run a find command. So for example, on my Mac, I have it under applications, VisIt app contents resources data noise.silo. And if you still cannot find this file inside your VisIt on your machine, you can simply download another zip file, bit.ly/VisIt files, which has a lot more stuff in it, including some data files, and you'll find noise.silo in one of the subdirectories. Okay, there are 2 packages for general purpose scientific visualization that we recommend to people. One is called VisIt, the other one is called ParaView. And both of them have these nice features listed on this slide, so they can visualize both scalar and vector fields, also tensor data, and tensors of tensors and so on. They can work with pretty much any spatially defined data. So data can be defined on Cartesian grids, on unstructured meshes in 2D, 3D, on particles, on polygonal meshes, on irregular topologies. So pretty much anything you can think of. And they've been designed, both of these packages have been designed to handle very large visualizations, going from megabytes to gigabytes to terabytes in size. And of course, if you want to visualize a terabyte-sized data set, you have to do it on a parallel machine. There's no way you can process and handle it and fit into memory on your laptop. So both of these packages have been designed to scale to a very large number of processors, so large computing facilities on HPC systems, to thousands and thousands of cores, and run in parallel. But you can also run them very nicely on your laptop. You don't have to run them in parallel. So you can run a single application, which will be both the client and the server, and assuming that you can fit your the data set on your laptop, everything will be run inside a single application. So both of these packages have ability to do interactive manipulation. You sit in front of the client and load the file, and then do some fancy things with this. And they also support scripting. So both of them support Python scripting, which is the main topic of today's presentation. So traditionally, we've been supporting ParaView. And for the past few years, we've been teaching ParaView extensively, so various webinars and hands-on face-to-face workshops at different universities. So I travel to different WestGrid institutions and give full-day ParaView workshops. So we haven't taught VisIt really so far, and there's no really good reason for this. So we simply had to pick up one of these 2 packages to focus to do training. But I know there are quite a lot of groups in Compute Canada, research groups, and in WestGrid that use VisIt visualization, and we want to support them as well. So starting this fall, we officially offer both ParaView and VisIt training, depending on what you're interested in. So in fact, tomorrow I'm giving a full-day visualization workshop at UBC, which is going to be focused on VisIt. Next week, I'm going to give a similar workshop at UVic. So if you're from Vancouver or Victoria areas, feel free to register for these workshops. They're free. We don't charge any money. And I think they're going to be very informative for you if you want to learn more about 3-dimensional scientific visualization. And if you are not from Vancouver or Victoria and you still want to see these workshops, either VisIt or ParaView, then just drop me a note and I'll be happy to arrange a workshop at your institution. Right? So a couple of words about VisIt. The development of VisIt started in 2000, and the first release was in the fall of 2002. So it's officially maintained by Lawrence Livermore Laboratory, and it was designed for to visualize results of a very, very large, massive computer simulations. And currently there are about 20 developers worldwide working on VisIt, so it's actively maintained. It's still being maintained by Lawrence Livermore Lab, I mean the main repo, but the developers are scattered all around the world. And the currently available, most recent available version is 2.11. You can download it as a source code and compile on your machine, or you can download it as binary. That way you don't have to compile it. So the binary is available for Linux, Mac, Windows, 32-bit, 64-bit. Just pick up the version you like. It has tons and tons of visualization features. So various visualization plots and operators, counters, meshes, isosurfaces, slices, projections, volumes, visualizing molecules, geographic data, and lots and lots of other things. And it understands over 100 different file formats. So if you can't import your file into VisIt, just send me an email and I'll be happy to help you. And as I mentioned, VisIt can scale up to very large supercomputers. So it uses MPI, message passing interface, underneath for a distributed memory parallelism on parallel machines. Okay. So VisIt has a very nice GUI interface. And I already mentioned ParaView at the beginning. So ParaView and VisIt have a very similar set of features. I mean, they're really competing packages. But if you're used to one, it's very difficult to switch to another because their GUIs are very different. They're both nice, but they're just very different. So if you're used to ParaView, you'll find it kind of difficult to use VisIt and vice versa. So I already started VisIt on my machine, and the default interface looks like this. So you have the main driver window, and then there's a visualization window. So let me just show you a couple of things you can do. So basically, you add a plot, you load your data. So I'll open the noise.silo dataset. Right here, noise.silo. So I loaded the data set, and then I will add a plot. So I'll plot a variable that is called Hardy Global. So I added the plot, and then I need to draw it. And this is what it looks like. So it's a three-dimensional plot. It's a three-dimensional visualization then you can interact with. And then you can do various things with this. For example, I can slice it, or I can add another filter. So let me do selection and clip. Then draw it. And so here I apply the clip filter to the data set. And as you can see, everything is interactive. And I can modify the properties of the filter. For example, double click on the filter itself. And then I'll see various attributes that can change. And it's all interactive. Okay? But today's webinar is about scripting. So I'm going to show you how you can run Python scripts in VisIt. Okay, so let me switch back to my slides. So VisIt supports a number of different interfaces. There are APIs, well, there are shells and APIs. Well, there's a Python shells, and there's also API for running VisIt commands in 3 languages, in C++, in Python, and in Java. And the nice thing is that you can actually run all of these interfaces separately. So as I'm going to show you in a minute, you can run the GUI and the Python shell at the same time. And what will happen is when with the GUI already running, when you start a Python shell in VisIt, it will attach to the VisIt session already running on a specific port on your laptop, and the two will run in parallel, interact with each other very nicely. So why do you want to automate? Why do you want to do scripting in the first place? Well, the obvious answer is you want to automate repetitive tasks. So for example, if you're doing visualization that takes 100 or 200 clicks, and drilling down into all menu items, setting all parameters in the GUI, you really don't want to do it every time. And scripting allows you to basically document your workflow in a code, and then this code can be run easily by you or by someone else. So for example, if your colleague has a similar data set, you just pass the VisIt Python code to them, and they'll be able to run it, perhaps with a few modifications, and then they'll be able to do a similar visualization or perhaps enhance your code. So essentially, it's a way of automating things and a way of documenting your workflows. And of course, if you're doing visualization on a large system, on a cluster might not have a GUI. So for example, it might not have an X Windows system, or in that case, you won't be able to open the VisIt GUI, but you'll be able to batch it, to run the script, perhaps as a batch job. Maybe you have a very large visualization that takes hours and hours to render, and then you just submit it, let's say, as an overnight batch job. You come back in the morning, and your visualization is ready without opening any windows. All right. So there are several different ways, excuse me, of running Python scripts in VisIt. One way is to do it from the command line. So from the Unix, Linux, or macOS command line, you can simply say VisIt, so path to VisIt. Then you pass a couple of flags, no win and a command line interface. So no win ensures that you do off-screen rendering without opening any windows. And command CLI simply stands that you're doing all processing in the command, in the terminal window, and then you pass the script name to it. And then if the script has been debugged and it runs properly, everything will run without opening any windows. You can do it either locally or on a cluster, and everything will be rendered very nicely. There are a couple of other ways you can launch Python scripts from the GUI. So in the GUI, if you go to Controls, Launch CLI, Launch Command Line Interface, that will open a Python shell in a terminal window, and it will attach to a VisIt session on a specific port on your laptop. So let me go back to the VisIt window. I go to Controls, Command Line Interface, Launch Command Line Interface, and I will start the terminal window. So I don't need this one. All right, so let me make the fonts a little bit bigger. And here you can simply type in commands. So this is Python, the usual Python 2.7 or something, as you can see. And here you can type VisIt's Python commands. The second way to do this, let me close the shell, is to go into Controls in the menu and calling command. And that will open what is essentially a notepad area or text editor with 8 windows. And in these windows, you can simply write your Python code, and then when you click on the execute button, the code will run. So very handy if you don't want to open the terminal window. There's also a record button here that will let you record any GUI operations and convert them automatically into Python scripts. And that's very handy if you don't know any Python, or if you're just not sure which VisIt's Python command you should use. You can simply do some sample, test visualization in the GUI, and then record it, and then you can save the script and then run it later on. So I'm going to show you an example. Let me just clear everything from this window, and I'm going to switch. So I'm going to record. Oops, sorry. I'm going to press the record button. So it does some stuff, opens terminal, which we're not going to use for now. So we're recording now, and then I'm going to, let me close this file. So reopen the file again, noise.silo, and then I will add a PseudoColor Plot of Hardy Global variable, Hardy Global is just the variable name. And then I will draw it, and then, oops, right here. I have too many windows here. So here's our visualization, and then I'm going to say pause, and then this will give me a Python script. Oh, sorry, not pause, stop. This will give me a Python script, and then you can actually run this Python script either from here or from another interface, from the shell, from the terminal shell, or from wherever. So let me just erase this visualization and show you that everything runs. So I'm going to run execute. And as you can see, the visualization was done very nicely. So let me delete this plot and go back to the slides. So there are a couple of other places where you can use Python scripting, but these are more advanced usage options, and we're not going to cover them today. So in one of them, in controls expressions, where you can actually, it's an equivalent of Paraview's calculator filter, if you're familiar with it. So basically, it lets you construct mathematical expressions to define new variables that you can visualize later on. And there are two ways of doing this in VisIt. One is to simply type in mathematical formula. The other one is to use Python scripting. So with Python scripting here in controls expressions, you will work with VDK objects, which is a much more advanced options that I want to talk today during the webinar. So we're going to leave it perhaps for a future webinar. And the second place where you can use Python scripting is in controls query. And that lets you, I'm going to show you several examples of similar things, not exactly this. So here, again, it's a more advanced options control query, which simply lets you query the data set. So for example, if you find the minimum value or maximum value or something like that. And here you also have two options. You can either do it through the GUI or you can do it through the Python interface. And with the Python interface, again, you'll be working with the VisIt objects, which is a more advanced options that we're not going to cover today. All right. So adding plots, we're going to work now with the interactive shell. And I'm going to copy and paste the following commands into the terminal shell. So let me close some windows that I'm going to use. Actually, this one, let me reopen just to double sure that it works, reopen the command line interface. I go to controls, launch command line interface. Here we go. Let me make this window bigger so you can see what's happening. All right. So I'm going to paste the following commands into this shell. I'm going to open the database. So essentially, I'm just loading the same noise.silo file. I'm going to add a PseudoColor plot, plotting the Hardy global variable, and I'm going to draw this plot. Okay, so I'm going to copy and paste these commands into the terminal shell. And let me open. So this is the view window, and this is the shell. So let me copy and paste. And as you can see, it worked very nicely. So here I have my three-dimensionalization of the Hardy global variable. Okay. So each plot in VisIt has a number of attributes, actually many attributes that control its appearance, and you can modify all of these attributes either from the either from the GUI, so simply double-click on the object on the plot in the pipeline browser, and here you see lots of attributes, or you can do it from the Python shell, from the Python interface. So to do this from Python, you need to first create a so-called plot attributes object by calling a function which is essentially a plot's name followed by attributes. So for example, PseudoColor Plot is going to be PseudoColor attribute. For volume attributes, it's going to be volume attributes function. For isosurface, it's going to be isosurface attributes, and so on. And then modify the attributes. I'm going to show you an example. And then pass these attributes object to the setPlot options functions if you actually want to make these attributes active. And then if you want to make them default, so there's another function which is called setDefaultPlot options that just makes them default for all future VisIt sessions. All right, so here's an example. I'm going to call PseudoColor attributes. I'm going to modify the properties of the PseudoColor plot that we already have right here in the visualization window. And so I'm going to pass the output of PseudoColor attributes function to the attributes variable called P. And then I can optionally print all the attributes. So you will see that in a second. And then I'm going to change 4 attributes. So minimum and maximum values. I'm going to set the color range from 1 to 3. So let's go back to the window. And you can see in the legend here that the full range of the variable goes roughly from 1 to 5.9. So from 1 to 5.9, I'm going to change that from 1 to 3. I set here the values, Pmin and Pmax to 1 and 3. And then I want to make this active. So Pmin flag and Pmax flag are going to be set to 1 and 1. So the idea of these min and max flags are that if they're set to zeros, then VisIt is going to use the actual data range of your data set. And if they're set to 1, then it's going to use the values that are set in the Pmin and Pmax variables. Okay, and then I need to actually make this work, I have to, so once the options are set, I need to pass the attribute object to the setPlot options command, and then things will change in the visualization window. So let me copy and paste that. So here's the visualization window, here's the terminal, and let me just copy and paste these commands into the shell, Python shell. So here we go. You see that the plot changed. Now we're plotting from 1 to 3. Exactly as the way it should be. And all values that are outside this range are simply saturated. So they're either dark blue or dark red. And so the visualization worked exactly as we wanted. So now let's revert back to the original color range. So all I have to do is simply set the min flag and max flag to zeros. And then the legend will, well, the visualization will default to the actual data range. So let me do this. And then, of course, I have to pass the attributes objects to the setPlot options function. So here's my visualization. It's really, really difficult to do this when I have multiple windows on my screen, but well, bear with me, so I'll try to show all the windows. So here's my visualization, and here's the shell. So I'm pasting the two commands, and everything worked nicely again. As you can see, now the range goes from 1 point something to 5.9, roughly. And remember that I had the print P command, well, actually P right here, which was printing out all the attributes. So here are all the attributes. There are, I don't know, 20, 30, 40 of them. There are actually quite a few. I can even modify all these attributes from the Python shell. All right, let's now pick a different color map. I'm going to pick the green color map. So here's the visualization window, default color map, and let me change to the green color map. So I simply modify the attribute which is called color table name and set it to greens, and then pass it to set plot options, make it active, and everything worked. All right. So I was pasting commands into the shell window, but that's kind of difficult if you have scripts that contain multiple lines. I mean, you can certainly copy and paste them, but it's much easier to simply call the script by its name. And there are multiple ways of doing this in Python, so I'm going to use the way simply call the source function. So I need to change the directory that contains the script. So my directory, this directory on my laptop. And then in all the scripts in this directory, they're included into the zip file that I mentioned at the very beginning of the presentation. So you have the full copy of all scripts. You don't have to record them from the slide. And you simply source that using the file name of the Python script once you're in the right directory. So let me change to the right directory. Here we go. So here's my Python shell. Changing to the right directory. And make sure I'm in the right directory. Yes, I am. I'm in scripts now. And then let's call a script which is called orange. So here's what the script does. It deletes all the existing plots and add a new pseudocolor plot of the Hardy global variable. It calls PseudoColor Attributes. Again, we've done that before. Then it changed the color table name to oranges, so set the plot options, and then it draw the plots. So essentially, we've done all of this before. The only difference is that we're setting attributes before drawing. So remember that before we already had a plot, and then we're making changes in some attributes and passing the attribute object to set plot options. Now we first call set plot options to set the attributes, and then we do draw plot. So I'll just simply gonna do source on orange.py. So source on orange.py, and that changed the default color map to orange, right? Now let's script an operator. So the syntax for operators is also very similar. Here is a file which is called addOperator.py. I'm going to source it in a minute again. So let's just go quickly through the file. So I delete all the plots. I create a new PseudoColor plot of Hardy global variable. I add an operator called isosurface. So that's simply for drawing isosurfaces of a given variable. So the variable is going to be called Hardy global right here. Hardy global. And then we draw isosurfaces using the levels. You will see how many levels there are. And then, simply we create an isosurface attribute object called isoAds, and then we'll modify several of its properties, right? So set the variables, set how exactly we're going to position the isosurfaces by levels. So simply we specify the number of levels where we're going to draw isosurfaces. The default is 10. So we'll see 10 isosurfaces, and then we simply set these attributes, make these attributes active by passing the attributes object to the set operator options. So now instead of set plot options, we'll have the set operator options. So very, very easy to understand, very clean interface. And then we draw the plot, and then we print all the attributes of the isosurface. So let me run it. I will simply paste everything into the shell. So here we go. We drew 10 isosurfaces. As you can see, it's a nice three-dimensional visualization with 10 isosurfaces. And then we see we also printed all the attributes of the isosurface operator, and there are 10 so attributes. So you see that the default value, the one we didn't change, is by default it plots 10 isosurfaces at 10 different levels. And then using the linear scaling, which of course we can modify to anything we want. So now let's produce 3 single isosurface plots at these specific values, 2, 3.5, and 5. So I have a script that is called 3surfaces.py. let me source this. Let me open the visualization window right here. So pay close attention to what will happen. Actually, let me minimize this a little bit so you can see better the visualization window. Okay, so I'm gonna paste the command, the source command, into the shell. And not sure if you saw that, if it played through video desktop, but what happened is that 3 visualizations flashed very quickly, and then now I see only the last visualization, the value at Hardy Global equal to 5. But these were not saved. So how to actually save the 3 surfaces? So to do this, there is an interface for saving windows. So there's another command which is called Save Window Attributes to create an attribute for saving windows, and then there are a number of options you can change. So let's save as a PNG file. So we can set the file name, output to current directory. If it's set to 0, then this is yes. If it's set to 1, that the output will be written into directory that you specify in the output directory variable. And then to actually make all of these attributes active, you pass them to the setSave window attributes function. Then you display a plot, and then you call the save window function to actually save the plot to the window. So the script that we're going to run is called save surfaces.py, and essentially we are saving everything to the current directory. And also, for some reason, I also decided to specify the directory by hand. And then there are 3 isosurfaces, so at values 2, 3.5, and 5. And then we essentially, after creating a corresponding isosurface, we set operator options, and then we call the save window command. So let us run this. So I run the save surfaces.py script, and as you can see, it was saved to 3 files in the current directory: iso000.png to iso00.2.png. Excuse me. And everything worked nicely, so the files are actually there, trust me. All right, so let's go to the next slide. How can you animate a camera position? This is very useful to know if you have a large visualization and you want to do things like zoom in on a specific region, or you want to rotate your object, or perhaps do fly-through. So we're going to do all of this. And it's actually very, very easy to do that. So before I go in there, let us create a plot, and let us set up a default view. So I'm simply going to delete all plots. I will create a Hardy Global, contour isosurface plot of the Hardy Global variable, and then here are some attributes of the isosurface plot. So I'm going to plot at the value 3.8, and using this color, and let me run it. So the script is called onesurface.py. Here's my visualization. And here we go. So this is the isosurface at value 3.8. All right. So let me run a command print view. So there is a function called getView3D, which will let you print all attributes of a given 3-dimensional view. So if I run that, you'll notice that there is a bunch of attributes. So there are 10 or 15 or so of them. So the important ones are actually all of them are important. So depending on what you want to do, you will change one attribute or some other attribute. So view normal here is view normal and view up are the 2 vectors that define the orientation of your visualization. And by changing these, you can actually change. You can, for example, rotate your object or just set a specific view or something like that. So let me run this script. So this script sets the control point. So basically, it sets a default view. So we create an attribute by calling the function view 3-dimensional attributes. We set the azimuthal angle to 0. So we're going to look at it from the equator, and then we set theta to 0. The azimuthal variable phi is 0. So yeah, so that's the longitude, right? And then we set the latitude to 0, so we're looking at the visualization from the equator. And theta is going to vary from minus pi over 2 to pi over 2, whereas phi is going to vary from 0 to 2 pi, so we just set both of them to 0 for now. And then we use a bunch of trigonometric functions to set up the view normal, and then set up several other variables. So let's just run this. Nothing will happen because this doesn't change the visualization. But we set up the default view. We set up the view called C0, and we're going to use it in a second. And yeah, so here's a side note that the way you zoom on a visualization in VisIt is you need to use the scroll wheel on your mouse, and it doesn't work very nice if you have a trackpad. So on my trackpad, I have trouble, basically I have to scroll up and down, but it's very jumpy, so it doesn't work very smoothly, and I prefer to set the zoom level either from the Python interface or simply go into control view and doing that in the GUI. You will see there is a image view or visualization view, something like that, option that you can change, right? So let me go to the next slide. Let's actually do camera rotation. So we're going to do that around the vertical axis. Phi is going to change in 300 levels from 0 to 2 pi, and simply we set the view normal attribute, and then we make it active by passing the attributes variable to the set view 3D command. So let me copy and paste that. So the script is called rotate around vertical axis, and here's my visualization window. And then let me paste the script in here. And as you can see, I'm not sure if it plays nicely through video, but I have very nice, very smooth rotation, 300 steps. The whole thing rotates very smoothly around the vertical axis, completing one full revolution. Right? So now we're going to do fly in and out, and here we simply change the attribute which is called focus. So focus, you pass to it 3 values, and we're going to change the very first value smoothly from 0 to minus 40, and then from minus 40 back to 0. You will see what happens. Basically, we'll just fly into the visualization and then fly back out. So the script is called fly in and out, and let me run it. Oops. So here's my script. And again, we have a very nice, very smooth feedback. I'm not sure whether it plays nicely through video, but you can always play it back later on your laptop. And very nicely, so let me just run it again. We're flying into the visualization, and then we'll fly back out. And then the next script I'm going to show you is called perspective.py, and we're simply going to change the perspective angle. So this perspective angle will go from 30 to 60 in 100 steps, and then back from 60 to 30 in 100 steps. So the script is called perspective.py, and let me run it. And as you can see, you're simply changing the perspective of your visualization very smoothly. So the front plane is moving towards you, the back plane is moving away from you, and vice versa. Let me play it back again. Here we go. And again, I apologize if playback is not very smooth through video, but believe me, it's very smooth when you play it on your laptop. Okay, so now let's do something cooler. So let's now animate 3 different effects in a single script. So the way to do this, I'm going to define, because in Python you can't change all attributes of an object by a single command. I'm going to define a function which will do this by hand. So simply, if I want to take a current view, remember the view was, for example, C0 here. That's the attribute, right? That encodes the view, all the angles and perspective and so on. So if I want to copy it to another variable, I have to do it one attribute at a time. So to automate that, I'm going to do that through the script, the function called copyView, which is simply going to copy A into B. To define this function, I will run the script called copyView. So let me run it. So things defined. And now I will set up 3 control panels. So the first control panel, I'm going to copy C0, the original view, into C1. And then I'm going to change the phi of C1. Basically, I'm going to rotate my visualization around the vertical axis by 90 degrees. Then I'm going to copy C1 into C2, and I'm going to rotate it around the horizontal axis by 30 degrees, so pi over 6. and then I'm going to change the focus. I'm going to fly into the visualization, starting from C2 and into the point called C3, right? Okay, so again, this is a definition in the script 3 control points, and it doesn't do visualization yet. So let's just run and define these 3 points, C1, C2, and C3. Okay, here we define them. And then finally, we're going to do visualization. So we construct a tuple of the 4 control points, so starting from the original C0, C1, C2, C3. And then we're going to define the corresponding positions in time. So they're going to be 0, 1/3, 2/3, and 1. So they're equally spaced in time. And then we're going to interpolate the tuple of the control points onto a finer mesh corresponding to a finer mesh in time. So basically, we're creating a mesh of 200 points in time, and then interpolating from the 4 original control points to a much finer mesh of the 200 control points, right here. And then we take each point in that mesh, and we pass it to the corresponding attribute and set it active with the setView3D function. So let me play it back. The function is called interpolate.py, and pay close attention to what happens when I run the function. So rotation around the vertical axis, around the horizontal axis, and then fly into the volume using the 4 control points. So let me run it again. Notice that I have interesting pivoting here. So after rotation, vertical rotation, I have nice pivoting here. And the reason for this is because I'm using a multi-point spline function, and that gives you a very nice effect, which I actually personally kind of like. So let me run it again. And if you want to see smooth playback, please just run the script on your laptop. And if you have any questions, let me know. All right. So this is all I have to say about animating the camera position. Now let's try to animate an operator. Actually, this is an exercise for you to do later on, but I'm going to show you the result of this animation. So here is a visualization where I don't animate the operator yet. So we're plotting the PseudoColor of Hardy Global, and then we modify. So we set the view to some nice view, and which is actually the same as the C0 view from the past few slides. Then we set the light attributes. So in VisIt, you can set up to 8 or 10, I can't remember exactly, lights, and you can set their positions, their spectra, and their brightnesses. And it's very nice if you, for some reason, you don't like the default lighting. And then we call up the clip operator. So that's the section with a plane, and then all points on one side of the dissection will be kept, and all points on the other side of the dissection will be thrown away. And so that's a nice way of showing slices while keeping the 3-dimensionality of your original visualization. So we set some values for the clip operator, attributes of the clip operator. So basically orientation and position, and orientation and position. And then we simply make these attributes active, and we draw the plot. So let me run this clip static function. Again, the output of the clip operator is PseudoColor. And the exercise is to try to animate the clip plane, moving it smoothly from the bottom to the top. And this is an exercise for you, but basically all I have to do is modify one of the attributes and then play it back smoothly. Here's an exercise. So do it at home after the class, and then write each image as a PNG file, and then at the output, at the end, you will have 100 or 200 or how many PNG files that can merge into a nice MPEG or QuickTime or AVI or whatever movie using any number of the third-party routines. So I personally prefer to use FFmpeg. So the options shown here, this is a command line in Unix, will create a very nice, very well-compressed, but very high-quality MPEG for movie that supports QuickTime as well. So let me just show you the result of the animation. So I'm going to play a script that you don't have. The idea is that it's an exercise that you can do yourself, and it'll just show you how the thing plays nicely, moving the slides from the clip plane from the bottom to the top. So here we go. Next, I'm going to say a few words about using queries in Python and, well, in VisIt Python and in VisIt in general. So in the GUI, you can do that via the control query command. So if I go to the VisIt GUI, I go to controls query, it opens a nice window where I have 30, 40, 50 so queries. They can use things like min max and memory usage and a bunch of others. So that's done by the GUI, and it's a very nice interface. But if for some reason you want to do that via scripting, you certainly can. So all of these are accessible via Python. And here's a simple example where I delete all plots, draw the PseudoColor plot of the highly global variable, then do the min-max query, so essentially probing the smallest and largest values of the data set. And then I print those values. And if you run the script, so let me just run it, query pseudocolor.py. You will see that it prints out these two values. So the question is whether these values are from the three-dimensional data set or from the plot, which are different things. So you don't see the all cells in the plot. You're currently looking at the outer surface. So do this value comes from the outer surface or from the full three-dimensional volume? So let us try to run this script. If we try to run the script, commenting out the plot command, so basically just run the same thing. And comment out the draw plots command. And if you do that, you'll get an error. So it will complain that you'll try to do min-max on a non-active hidden plot. So the plot doesn't exist, it's hidden. And basically, it will not run the query command. It will give you an error message. So this implies that the min-max are run on not on the full three-dimensional volume, but on the outer surface of your visualization. At least that's what you would think based on this error command. But that's actually not true. So here's another script. Let's just run it. Query contour.py. And what we do here is, so let me just run it. And what we do here is we erase all plots. Then we, instead of a pseudocolor plot, we do a contour plot, so isosurface plot of the same highly global variable. So the plot looks very different, right, to the previous plot. And then we use the same query min-max command and print the values. And it turns out that it prints out exactly the same output as before. So this is really strange because we needed, so remember, we need a plot to do the query. So it looks like we query the plot, but we actually query not the plot, but the three-dimensional, the actual three-dimensional data set. So this is an inconsistency, and I don't have any good answer for why this is the way it is. It's just up to the authors of a query. So it's completely up to them how exactly they ran it. So whether you query the original data set or the plot. And some of them query the original three-dimensional data set, some of them query the actual two-dimensional plot. So you have to be very careful when you run these queries. So make sure, read documentation, make sure that you print out exactly what you want. So here's an example where you query similar commands. So we construct a bunch of we draw a bunch of slices, and then we march through the slices from bottom to top, and then at each slice we run a query, and then first the min-max query, and then the weighted sum query. And it turns out that the min-max query is actually probing the three-dimensional data set, whereas the variable sum query is probing the output of the slice operator. So be careful when you run these queries. You have to make sure you read documentation and understand exactly what they do. So if you, let's just run this command, query slice, and you will see that we're doing a slice. Now it's a two-dimensional slice, so it's not showing 3D, it's just a purely two-dimensional slice. And as you can see, min-max at all slices is exactly the same, whereas the weighted sum is different. So the weighted sum applies to the output of the slice operator, whereas the min-max applies to the original three-dimensional data set. All right? So be careful. That's all I want to say. All right, so I already mentioned recording GUI operations to Python scripts, so it works very nicely. I give you an example at the very beginning. So be careful when you do this, because sometimes the recorded script, automatically generated script, will not be what you expect. One example is a save movie command. So you can save movies, generate and save movies from a file save movie, a GUI interaction. And if you try to script it, it will produce a perfectly normal Python script. The problem is that it will repeat the same Python script for each frame of the movie. So if you have, let's say, a time-dependent data set with 1,000 time steps, then it will produce a script where the basically plotting on each frame and saving each frame will be repeated 1,000 times, which doesn't make any sense. So be careful when you use the Python recording. So in this case, you have a time-dependent data set. What you really want to do is script a single plotting and saving a single frame, saving as an image, and then wrap it into a Python loop where you have to make sure that at each loop iteration, you read a new file, a new frame, and then you write a new image at the end of each loop iteration. So, and then you get 1,000 or how many PNG files that you can merge into a movie later on. So you have a nice exercise for you. Again, you can do that in the during the webinar, but if you're curious, feel free to do this after the session. So I have a couple of data sets. They are right here. One is a standard data set from VisIt tutorial, so aneurysm data is actually very large, more than 300 megabytes. The other one is from my full-day VisIt workshop. It's called 2D, so the files are called, let's say, in data set evolution directory called 2D, three digits, .vtk, and feel free to play with this and try to see how Python scripting works for animation in VisIt. All right. So there are a number of other things that I can't cover here and that I haven't mentioned. So a couple of things I mentioned already, where you can do Python scripting in VisIt, so the expression editor and the query editor. But there are a few other things where you can use Python scripting in VisIt. So one of them is you can set your own buttons in the VisIt GUI, and you can create custom Qt GUIs and interfaces based on VisIt. So, for example, if you want to have, I don't know, some sort of material analysis where you calculate porosity or something like that, and you want to script it in Python, and then have a nice set of buttons for calculating porosity and perhaps something else in the VisIt GUI, you can certainly do that. So VisIt allows you to do that. The other place where you can use Python scripting in VisIt is for whenever something interesting happens in the VisIt GUI, pass that something interesting to a callback function, and then process that something interesting inside the script. So a couple of examples. One is, let's say if I have a time-dependent simulation, let's say of galaxy formation, where you have galaxies forming in the volume, and then you want to zoom in on different parts of the volume at different time. So you can actually write a script that will capture the time slider. I haven't talked about time sliders, but in the main GUI windows, there's a time slider. If you have a time-dependent data set, you can actually play with this slider, and you will visualize different time steps in your simulation. So while you're playing with the time slider, you can actually write a function that captures the time step, the time step number, and passes it to Python script, which will zoom in on a specific region. So for example, if you know that at a certain point in your galaxy formation model, you form an interesting galaxy in one part of the volume, and then you want to look at a different part of the volume at another time, you can certainly script that. And then the only thing you'll be playing with inside the VisIt GUI is going to be the time slider, and then so you point it to different times, and then VisIt will automatically zoom in on an interesting feature in the volume at that specific time. So another example is you can write a script that, so when you're clicking on a visualization with a pick tool, so I haven't mentioned the pick tool, but it's one of the things in the GUI you can do to probe the value of a function under the mouse cursor. And then you can write a script that will take all these points that you generated in the GUI and then do something to them. So process, I don't know, save them to a file, or process some nice plot, or something like that. So, and again, I can give you many more examples where this sort of callback function is useful. And all of this is done by Python scripting. All right, so a couple of really short examples I want to show to you, the ones I mentioned in the abstract, and you can do both of them via the GUI, but since this is the webinar on scripting, I want to show you the Python scripts. So one is on showing terrains in 3D. So there are many places online where you can download terrains. One of them is from Google Maps. The other one is from Natural Resources Canada, which has full maps, full topographic maps at 50,000, 1 to 50,000 and 1 to 250,000 resolution for the entire country, Canada. The interface, so here's a link to the data, but the interface is really bad from the 90s, so it's really very hard to find the exact map you want. So I downloaded a map of a part of coastal British Columbia near Vancouver, and I'm going to show you, I'm going to try to visualize that. First in 2D, and then in 3D. So here's the script for doing that in 2D. So basically, I open database. It's a DEM, digital elevation map, two-dimensional file. So VisIt can understand these files natively. And then I'm simply going to upload the height variable in PseudoColor and then draw the plot. Excuse me. So let me run the command. Let me erase the plot. So delete this one, close the data set, yep, and then go back to the shell, and then just paste the commands, the 3 lines. And so here we have a, let's see, do I have it? Okay, so here we have a nice visualization of the topography, coastal British Columbia near Vancouver, but it's a 2-dimensional map. So would be nice if you could do the same in 3D, and you can actually do it very easily. There are a number of ways you can do this in VisIt. So one way is to use a couple of filters. So here's a script that does it. So one is an elevate filter, will actually bring the map into 3D. For some reason in VisIt, the scale offset is not controlled in the elevator filter, but it's controlled in another filter called transform. So basically I have to apply two operators. One is called elevator to make it 3-dimensional, and the other is transform, where you turn on scaling and then you modify scaling in the Z coordinate along the vertical axis, so that it doesn't pop out as much. So you will see what I mean. So let's just run this script. So that's saved in a file called terrain3d.py. So here's my visualization window. And then I source the Python script. So here it is. And as you can see now, I see a very nice, it's a 3-dimensional visualization, so I can actually interact with it. And shadows are turned on, so lighting is very nice. As you can see, it's really a 3-dimensional, very nice 3-dimensional visualization. And then you can do this to any terrain data, right? Whether it's DEM format or some other type of format. So very often when you visualize maps, you also want to plot some vector information off top of maps. So things like buildings or roads or country boundaries or something like this. So there's a way of putting that into 3D as well. And there's a nice tutorial linked here that shows you how you can do that in VisIt. All right. So the second small, actually, the last small example I'm going to show you is molecular visualization. And so there are a number of things you can do with molecules in VisIt. So VisIt is a general purpose tool that was not designed originally to handle molecules. But there is one plot that is called molecules that will let you visualize atoms and bonds between atoms, and well, in different ways. And it's very basic compared to VMD. So VMD is a domain-specific tool to visualize the output of molecular dynamics. So VMD stands for Visual Molecular Dynamics. And so VMD is really, really fancy. VisIt's molecular visualization is nothing compared to it, but it still allows you to visualize atoms and bonds and visualize it in different ways. And then, for example, if you have, if you have a quantum chemist type initial calculation, and in addition to the molecule, you have, let's say, you solve the Schrödinger's equation, so you have a wave function or probability density function in 3D. You can actually superimpose that as a volume plot, and then we'll have very nice output showing both the molecule and the 3-dimensional wave function. So I did some benchmarking of molecular visualization on my laptop in VisIt, and it turns out it takes 4.5 seconds roughly to visualize 1 million atoms at medium quality, which is not that bad compared to VMD. So it's probably a fraction, I don't know, something like 20% or 30% of the speed of VMD. But it's nothing to sneeze at. You can certainly visualize a very large atom. So for example, an HIV virus shell contains 64 million atoms, and you can visualize it within 4 or 5 minutes or so on a single laptop in VisIt. So that's not interactive visualization. I mean, I have to script it, but if you throw a bad job on your laptop or on a cluster, you can certainly generate 100 or 1,000 frames and have a very nice high-resolution movie at the end of this visualization. So I'm going to show you a simple example where I don't visualize 64 million atoms. I visualize 12,000 atoms. So this is one of the standard files that came with VisIt tutorials. You can download it from the VisIt website, and let me just run the script. So basically, I open the PDB, which stands for Protein Data Bank file format, encoding a molecule with 12,000 atoms, and then I draw atoms, set things like radius of an atom and the sphere qualitative medium, and then so the radius, and then draw bonds, medium quality, and here's the bond radius, and I'll use this color map. I turn on legend, and then I make all these options active. So let me draw this plot. The script is drawmolecule.py. Oh, it complains it requires two-dimensional data. So what I have to do, I actually need to delete this plot. Sorry, I delete this plot, close the data set, and then let me try to do it again. All right, well, so here we're in 3D, right? So here's a nice visualization, and you can actually zoom in. And as I mentioned before, zoom in doesn't work very nicely on the trackpad, but still works. And you see that I have a bunch of options, and you can certainly change them via the Python script or via the GUI. So in the GUI, if you double click on it, you see how you can modify atoms, you can modify bonds, you can modify the color map, opacity, and so on. So that's essentially all I wanted to say for Python scripting. So again, it's really, really useful to know how to script things in Python if you want to first automate repetitive things, and if you want to document your workflow either for yourself or for your colleague, or if you want to do visualization on a cluster in batch mode. So you have to know how to do batch rendering with Python and VisIt. And this is my last slide. So basically, summarizing everything I've said before, I really, really like the VisIt Python interface. And if you compare VisIt Python interface to previous Python interface, in VisIt it's actually much, much nicer, in my opinion, because it's much cleaner. There are fewer commands, and all command options are it's very clear what each command does. And then there's a recording tool if you don't know any Python. So you don't have to know Python to start programming in VisIt Python. Simply use the recording tool to generate template scripts, and then modify them, and modify one thing at a time, make sure that it works, and then simply adapt your script to do exactly what you want. So are there any questions? We have only a few minutes left for questions. So you can either type your questions into the chat window, or just make your audio, unmute your microphone, and then that way I'll be able to hear you. So any questions? Those of you watching via the web stream, as Jana mentioned in the beginning, you can send your questions via an email. I can't remember what it is, info. I can't remember what it is, but I hope you have it written down. Yes, info@westgrid.ca.
Currently, we have no questions by email.
Okay, great. So yeah, so if you send me an email or info@westgrid.ca, I'll be able to answer a question by email later on. So thanks everybody again. Just a reminder, we have two workshops, one tomorrow, a full day workshop on VisIt at UPC, the other one at UVic next Tuesday, next week, and we have all the details on the WestGrid website and in the slides as well. So thanks again, everyone, and I hope to see you in the workshops.